Hello, everybody. Good afternoon. My name is Christopher Petrone,
My name is Ben Zilber.
and we are a part of Seismo 6 Engineers. That's our senior design team, led by our faculty advisor, Dr. Malouf, and we will be presenting on behalf of our group on our project, A Mast Building. So we'll first start with an overview of the project, going over an abstract, then showing the architectural drawings, talking a little bit about our design process and our initial framing, and then going into the actual design of our structure, which results in our final structural drawings, and then concluding with the Q&A. I don't know if it's lagging for me, but the slides aren't changing.
Okay, well, I'll do it.
There we go. Okay, so for this project, we have been contracted to serve as a lead consulting structural engineers for a multi-family dwelling structure. And the proposed scope of this project includes a design analysis of the structure, as well as to provide structural calculations and drawings. So we have been provided the architectural drawings, and the location of the project is actually in Venice, California, as shown in Figure 1. So this is our west elevation architectural drawing. We can see that it's a 3-story structure. And obviously what sticks out is its facade or mask. Given the current time, the architect believed that it was a great little thing to add to the structure. And going to our next elevation, we can see that this mask is just on the west side of the building. On the east side of the building, it's just a normal finish. But we do have pitched roofs with vaulted ceilings. And another thing to note is the garage opening in the bottom left-hand side. Going next to our north and south elevations, we can see again that these units do have balconies, and that on the south elevation, again, there's that opening for the garage. So this is the existing site. There's a building there with a dirt patch. So a lot of it's undeveloped. And so the architect believes that it's a good idea to have the building here. Going to our next slide, we can see the first plan for the floor. We see that in this floor plan that there are two units. In total, the building has 3 units. However, on the first floor, it's only 2 units because where the third unit would be, there's actually a parking lot there. That's where the structure is. And then going into the second floor plan, this is where all three units are present. And this, the architect designated more of this as the bedrooms, and with bathrooms and powder rooms and all of that. And then going into the third floor, this is the proposed living room. And we can see this is where it's a very open area, very nice. There's balconies, and then with the vaulted ceilings, it's going to give a very nice ambiance to the entire structure. And then lastly, going into the roof plan, we can see again, there are the slopes, and it does flatten out. It's not completely pitched. In between those two, I guess, ports or boxes to the right, there's a little flat area for the AC units to be installed. So now I want to talk a little bit about the theory behind our design. Before we even started with the design process, we kind of sat back and thought what would be the best approach for our structure. Ultimately, we decided as a group that type 5 construction would be a good route, just because it's very common here in California. And so this means that we would use a combination of steel, wood, and concrete for our structure. For our need a flexural design, a lateral and upper load path, and with the roof, and work our way down. And in that process, to achieve reasonable dead loads for each floor, and then also research proper live loads that needed to be applied. And then lastly, we wanted to ensure that certain elements are being brought down, quote unquote, to the floor below, such as columns or hold downs. So that's what we wanted to achieve. And the way we did that was with the provided architectural drawings. We layered everything on top of each other and drafted it as one in AutoCAD. And then within that, we created layer states. So in the top, if you go back and to the AutoCAD. In the top right, that's we see everything kind of just mixed up together. And then at the bottom is where we have the just one layer state for itself. And so that ensures that we're not placing columns in the middle. On to our red lines. That's and before we even did the drafting, we printed out a set of plans for each member and drew red lines as to kind of just get a general idea of where we're placing our shear walls, what direction we're running our joist, our beams, and then yeah, just figuring out basic framing elements like that. And then on to the next slide, we see the framing plans for the second floor and the foundation. Again, just figuring out the general idea of where our shear walls are being placed, directions of joist, and then our foundation, just getting a rough idea of what type of foundation we're using in terms of footings, pads, grade beams, all of that.
Okay, so to design the building, we have to get the members, and to design the members, we have to get our loads. So on the right is a tabulation of all the different variables we applied for both lateral and gravity loads. So gravity loads, we have dead loads and live loads. Dead loads is the self weight of the structure and any static object on the structure that's bolted and not moving. And then for live load, that's any movable load such as furniture or hazardous areas like the balcony or the garage. So to design for gravity, the process is, as Chris mentioned, we have to define our member placements on the architectural plans, like the joists and the beams and headers. And we also have to make sure that the beams and headers land on another member or column, because you don't want to have a beam sticking out from a wall and then stopping in the middle of a room, because that's dangerous. And then we perform load analysis using ASD by applying a factor of safety. But the way we did that is we went on Excel and we applied our dead and live loads to the length of our proposed beam. And then we found the max moment in section modulus. Then using the section modulus, we chose a size. For example, if it was wood, we went to the Douglas fir tables and then we compared the moduluses, take the bigger one. And then we would check the size, and then we would check the on-center spacing, which you can see in figure 3. And what on-center spacing is in figure 2, if you look, that's the gap between the joists. So that tells you how many joists you're going to have in a single length, so you don't have to draw multiple joists in one AutoCAD. And then here's an example of our calculations through Excel. Figure 4 is an example of us using Weyerhaeuser's Forte web program. And what that program does is it lets us input our specific loads, and Weyerhaeuser's program, it analyzes our loads based on their product, so their specific joists, TJI and PSL. So those are the ones we chose for that. And then on the bottom is an example of the Douglas fir beam. We got that using what I explained on the previous slide with the modulus. And then if the beam couldn't handle the load because it was wood, we instead used a steel beam using the AISC manual, the beam section. So onto lateral design. So lateral is split up into 2 sections, seismic and wind. For seismic, you have to utilize online resources to get the properties of a site plan. Then you have to perform calculations from ASC 7-16 to get the base shear, which is the strength of the foundation or the bottom of the structure. Then you get a section of the building to get its average weight and combine it with the base shear and then apply that as a load to the structure, which is your seismic load. Wind is similar, but instead you're getting the velocity pressure, and that's just getting a bunch of other variables from 7-16. Then you apply to the height of the building as your load. And typically seismic is a lot heavier than wind, so you're going to use that to govern your design. So here's an example of seismic design. These are all the variables, the site information, you get that online. Seismic response coefficient, you calculate for that. And then finally, you get that all for base shear at the bottom. And then here is how to do the wind pressure. And then here we see that our base shear was 79 kips and our wind force was 55. Since seismic is greater, that one will govern the ladder design. So here to strengthen the building laterally, we have to include shear walls. And to get shear walls, we look at our plans and then we find the walls that are 2-to-1 aspect ratio, which is width and height. And then using the partition of the floor, that is the height of the wall above and below half the height. we get the weight, and our total weight for the third floor was 118 kips, which we then included here for the third floor to get 6.07 kips, which is the seismic force of the individual shear walls. Then to do that, to get the shear walls on the section, we find the length of the shear walls, and then we use our third floor seismic force, and then we design the hold downs, and the hold downs we used were Simpson strong ties.
So now we're going to discuss a little bit about our final framing plan. We're starting with our foundation plan. So we used continuous footings for all of our exterior walls as well as our interior walls. And then for our columns, we use pad footings. And then because of the garage and the obvious openings, we aren't able to use shear walls. So we used moment frames, and in the east-west direction, we used a 2-bay ordinary moment frame. And in the north-south direction, we used a 1-bay moment frame. And those are kind of denoted by
Are you there, Chris? All right, well, this is the legend for the actual drawing. The dashed lines mean wall above and the filled-in lines mean wall below. The next is second floor framing plan. The main problems we had with this framing plan was on the bottom left, between sections 4 and 5 and A and C. We had this very long steel beam that had to be cantilevered, so that turned out to be a very big size. Then here is indicating all our beams such as PSL. And then this is typically the same type of plan you see for every floor. So it'll just be copied over again. So here's this third floor framing plan. There wasn't really anything too hard about this. We just had to section off some of the beams because we didn't want the joist to be too long. For example, between D and E, FJ1, there's a PSL running orthogonally to it, so we wouldn't have to extend it all the way to the header above. Then the roof framing plan was generally simple. The only thing we had to do was between section F and G, we had to install a steel beam because that part to the left of the beam was flat. So roof rafter 1 to the right of it was at a slope. So we had to stabilize that. And then here are all the individual details for each section. Like, for example, there are connections and foundations. Here are the diaphragms, for example, and footings. And then lastly, these are the moment frames that we used in the previous slides. And in conclusion, the way we accomplished this was just general teamwork. Every Monday, our team Seismo 6 would meet after our senior design class, and then we would just divide certain tasks and work on it together. And the way we really got work done was through our collective Google Drive, where we uploaded our calculations, our drawings, and then on our Google Docs, we could ask questions in real time, which was great, along with Zoom. And then one thing we learned for this project is that printing out our actual architectural plans was very useful because we could just draw up our sketches instead of having to go through AutoCAD and get everything ourselves. And then the codes we used were ASC 7-16, California Building Code 2019, and then AISC Steel Manual, the Concrete Manual. We used AutoCAD, Microsoft Excel, RISA 2D and 3D, and then Weyerhaeuser Forte Web. And that was our presentation. Thank you. Any questions?
Yes, I have a question. I have two of them, actually. Well, it's going to be one. So with your roof, the way it's kind of pitched, how is that relevant to the buildings next to it? And is it meaningful to have that kind of roof an extra cost if the geographical location of this structure would be impacted by the surrounding buildings because Venice Beach is a very densely populated? Can you elaborate where you found this site?
Where we found this site specifically, it was assigned to us for our senior design. I'm not sure why our professor picked it. Chris, if you're there, do you have any insight on that?
Yes, I'm here. Sorry, I had technical
Can we answer the second question until Chris is working?
He's breaking up. It was only one
Um,
question because you did address liquefaction.
Yes,
Or seismic.
Ben said it was everything was the architectural drawings, the location was all provided to us. So of the USGS website. Can you guys hear me now?
Yeah, you sound good.
Okay. But yes, I guess I cut out as basically it's just as Ben said, we were provided the architectural as well as the location for this project. So we didn't have any power in determining its location.
Okay. Thank you. It was only one question.
From the judge.
You
I have a question.
addressed the second one. Thank you.
Okay.
Yeah, Shasing, go ahead, please.
Yes, my question is on your grid line 5. You have a moment frame and a shear wall system on the same line, and both of them have a different drift. Did you look into that consideration and kind of made sure that the building will perform per code? I think it's on first level that you have that moment frame and the shear wall on the same line.
Correct. Yes. For that analysis, we did add the I don't know what the exact term is, but we added the 30% in the orthogonal direction to both to kind of account for that. We did not calculate drift for the shear walls. However, we did for the moment frame, and the moment frame was within standard. And that drift we did calculate using ASC 716 that in chapter 12, using those equations in there.
Great.
Great. Any other questions? I guess we can open the floor now. Anyone else? I don't see anything in the chat or the Q&A.
Just one question about the footings. Could you review the footings for me? Particularly the single footings, the column footings. You had a table.
Table, okay. What slide that was, Chris?
Yeah, it should be in the foundation plan. It's the schedule. A little bit above.
Oh, okay, there we go.
You're right.
Yeah.
So just remind me I can barely see it, but the size of the footings, those are single column footings, is that right?
Correct. Yes, and the number within the octagon represents its size in terms of like square feet. So, for example, a 2 is a 2 square foot pad footing. A 5 is a 5 foot square footing pad footing.
And that was my basic question. So, do you consider a 2 by 2 footing a sufficient size? That's almost as large as some of the beams or the columns that are being used.
2 by footing in which location specifically?
I can barely see the drawing, so I just saw it on the schedule. And so where would you use a 2 by 2 footing, a 2 foot square footing? It's marked number 2.
Correct. Yes. A lot of those are for interior columns, like our 4 by 4 posts, our 4 by 4 HSSs, or our 6 by 6 HSSs. The larger pad footings are more for the moment firms.
Okay, thank you.
Oh, sorry. I'm cutting. Oh,
I got the drift, so it's okay.
Time for one last question, if there is one from anybody. Okay, I don't see anything, so I want to thank Amass Building. I also want to thank all the teams that presented in this session. Special thank you to all of our judges, Michael Dipsia, Shahseen Hussain, Michael Manukian, and Lisa Sachs. Again, thank you for all the faculty advisors and everyone else who worked on the projects. You guys did an excellent job.